Now we prove Cauchy's theorem for a finite group G. If G is abelian group, we have already established. Now we shall assume G to be a non-abelian group. Now again, as before, the proof is by induction on order of G. And because G is non-abelian, we'll have to have order of G to be 6 because the lower order groups are all abelian. So when we have order of G to be 6, G has to be S3, and there exists an element in S3 of order 2 as well as 3. So this element 1, 2, when we consider an S3, order of that is 2, and if we consider this element, this permutation, order of this is 3. So in the case of S3, we have the result to be true. So if order of G is 6, the result holds. Now we shall assume the theorem to be true for all groups of order less than order of G, and H be a subgroup of G, which is a proper subgroup of G. Then in that case, there are two possibilities. You have a group G, in that you have a subgroup H. So when P divides order of G, you can have your P dividing order of H, or P does not divide order of H for this proper subgroup. So when we have P dividing order of H, as order of H is less than order of G, by hypothesis, in H we can have an element of order P, and hence in G also. Now suppose P does not divide order of H for any proper subgroup of G, that is, no proper subgroup of G has order divisible by P. Now we will consider this class equation. We have order of G to be summation order of G mod n of A. Now we have those elements G in G, we divide that as those elements which are in Z of G rather, center, and those elements which are not in. So when we consider this, in this case, we know that whenever A belongs to Z, we have n of A to be the whole of G. When G is finite, order of n of A is order of G. So we have the number of elements in Z of G. If it is denoted as small z, then those elements which correspond to this, we will have that here. They are accounted here, and the rest we have here. So when A does not belong to Z of G, when A is not in Z of G, then you cannot have this to happen. So we have this case separately. Now we notice that when we consider order of G mod n of A, because G is a finite group, we have order of G upon order of n of A. So when we have this cross multiplying, we have order of G to be this, and n of A being a subgroup of G, proper subgroup, n of A being a proper subgroup of G, P will not divide order of n of A. So when we have P dividing order of G, and P does not divide order of n of A, naturally it has to divide the other one. So we have P dividing order of G mod n of A. Now since P divides order of G, and P divides order of G mod n of A, for each A satisfying this, P divides the whole lot. So P divides this, and so P must divide Z. So this means that P divides order of Z of G. So this means that Z of G cannot be a proper subgroup of G. So if Z of G is not a proper subgroup of G, means Z of G should be the whole of G. But in this case, we conclude that G is abelian. When we have, because in Z of G, all those elements which commute with all the elements, when that equals G, we have the group G to be abelian. So that's a contradiction, because we have assumed our G to be a non-abelian group. So there exist proper subgroups in G whose order is divisible by P. So definitely in that case, we will have by corollary to Lagrange's theorem, elements in that group will have its order P, and so in G also, So by induction hypothesis,